Friday UTIG seminar. So today we are hosting Derrick Lampkin, who is a cryosphere scientist working as an assistant professor at the Department of Atmospheric and Oceanic Science at the University of Maryland. He did his PhD at University of Arizona in 2005 and got a couple of positions at Penn State University and University of Colorado in the meantime. So he's especially focusing on supraglacial hydrology over ice shell, and especially in Greenland, and how this hydrology could be rooted down to the bedrock through fractures, moulins, or crevasses, because this has an implication of the ice shell stability and eventually to the delivery of material to the ocean that contributes directly to the sea level. And he's going to present today a summary of his recent work regarding the Greenland's shear margins in a warming climate. You can go ahead, Derrick.
Thank you. Thank you, Cyril, for a wonderful introduction. I want to thank you all for this opportunity to have this time to spend with you to talk about the work that I've been doing on water and shear margins. So it's a great pleasure to be here and a great honor. Thank you. I'll start off by saying everything that I'm about to talk to you about was the result of a massive accident. It turns out that for quite a bit of time, I was largely focused on understanding what was happening in the supraglacial environment, largely related to supraglacial lakes. And we done everything we could to examine these lakes. We were mapping lakes, we were examining their distribution. This was early off when people were trying to estimate the volumes of water that were associated with these lakes, their drainage behavior interseasonally and from one season to the next. We had done work in examining what their distributions were, controlled by the basal topography and the capacity for basal roughness structures or roughness elements to be able to translate through various ice thicknesses to influence where catchment basins could occur. And during this time, going through copious amounts of satellite imagery, examining these supraglacial features, we started to notice that water was ponding in a very peculiar place. Much of this work was focused in the extramarginal fields outside of Jakobshavn Isbræ, which is a major marine-terminating outlet glacier in west central Greenland, largely responsible for draining, approximately 7% or so the total ice volume, total ice discharge by volume from the Greenland Ice Sheet. So Jakobshavn has been a very important outlet glacier and has been heavily studied over the last several decades. So that was a place that we were naturally interested in examining the effects of supraglacial water on ice dynamics and on overall mass flux and discharge. And we started to notice that water was ponding in places that seemed relatively unexpected. And that was in the heavily crevassed shear margins of Jakobshavn. The Jakobshavn is peculiar in a lot of ways. It's situated inside of a deeply incised basal trench, subglacial trench. It's because of the orientation of the bed, its driving stresses are exceedingly large, and they're largely balanced by resistance along the sides, along the margins, as well as the bed. A lot of work has been done for people to try to constrain what the partitioning of the momentum balance is throughout Jakobshavn in terms of how much of that momentum is partitioned into friction in the margins versus the bed. And there's still ongoing debates about, mythically thick till beds at the base of Jakobshavn and whatnot. So that's an area of active research. Largely, we started to become very curious about, one, how water was able to pool within the shear margins, which are heavily crevassed. And also we noticed that these features were draining in very similar ways that were observed in the extramarginal field with large, cohesive, and well-deleneated supraglacial lakes. So that opened up a whole range of very interesting research questions about how do assemblages of water-filled crevasses behave, especially in a very highly dynamic area like Jakobshavn shear margin. And more importantly, what is the dynamic influence of squeezing water in one of the most critical places within the ice sheet system, where a large proportion of this momentum is accommodated for a major marine terminating outlet glacier. What I'll do in this talk is kind of walk you through a summary of work that we have published over the last 10 years or so that kind of give us a highlight of some of the insights that we gained from studying the injection of meltwater into a shear margin system like Jakobshavn. And it has very interesting implications for other outlet glacial systems throughout Greenland with varying degrees of different glaciological contexts where meltwater present at the surface in similar kinds of structures that drain and potentially deliver water to the bed may have similar kinds of implications for influencing the dynamic and overall mass flux from these outlet glacial systems. So yeah, we're largely familiar with the big picture here about why we care about Greenland, why we care about these large ice sheet systems. Obviously, we're enamored with understanding how the mass balance of these large ice sheet systems respond in a warming climate. Of course, marine terminating outlet glaciers are most significantly important in Greenland, but there are other glacial systems like in Antarctica, where West Antarctic ice streams are important in regulating the mass flux out of central West Antarctica. And more recently, appreciable focus on Pig and Thwaites, Pine Island Glacier and Thwaites Glacier, which are been characterized as exceeding a water instability criterion, which means that we're on the precipice of potentially rapid mass loss out of those glacial systems as the terminus of those systems retreat deeper into a deeply incised basin in the interior of West Central Antarctica. And so this is our common understanding about the reconciliation of multiple measurements of the assessment of mass balance for Greenland and Antarctica. And obviously Greenland has been much more aggressive in its mass loss, largely through these, potentially through these marine terminating glaciers. When we first started this work, there was substantive debate between two respective communities in the ice sheet, within the ice sheet community about what proportion of mass loss is driven by solid discharge through these marine terminating glaciers, discharging mass through ocean fjords and making a contribution to sea level rise versus direct melt runoff. And that debate still rages on. Largely, we've come to understand it's about a 60-40 split, where a large proportion of mass loss is due to direct runoff at about 60% and about 40% due to a solid mass discharge out of these marine terminating glaciers. So the dynamics of these outlet glacial systems, these marine terminating outlet glacial systems, are very important in regulating the mass flux and the overall contribution to sea level rise. This is a classic graphic that gives you a standard cross-section of a marine terminating outlet glacial system commonly found throughout Greenland. It's characterized by a coupling dynamics between an adjacent ocean or fjord with the terminus of the glacier. A whole host of very interesting and significant processes happen at the terminus. that promote the calving or breaking off of ice that results in the discharge of ice from the glacial system. The condition of the water in the fjord has substantial influence on the calving process, as well as near upstream processes that influence the overall force balance near the calving front. Those in combinations contribute to a wide range of different observations in frequency and total mass discharge at the calving front. And that's an area of current research across the community. As we move upstream from the calving front, we have ice dynamics that are associated with the influence of the supraglacial environment. So the ponding of meltwater in the summer allows for the proliferation of a wide range of hydrologic structures like lakes, supraglacial channels that are responsible at various hydrologic scales for filling these basins with water, as well as for transferring water between basins or between lake basins, as well as supraglacial channels that allow for the transport of surface melt water into crevasses and fracture systems that facilitate the delivery of that melt water into in-glacial systems and the subglacial hydrologic environment. So our larger research questions about water and shear margins were really about, for the particular features that we've observed for the Jakobshavn system, was what is the spatial distribution and drainage behavior of meltwater in the shear margins? What impact does drainage from shear margin ponds have on regional ice flow and mass flux? And what is the relative contribution of shear margin lubrication and calving have on extramarginal ice flow? Now, that last question, it gets to something really quite peculiar, and that's in large part the prevailing conversation we're having in the community about how much of the overall mass flux that we're seeing out of these outlet glacial systems are forced by the encroachment of warm water, shelf water that find their way into these fjords and enhance the calving process. It has largely been understood by a large proportion of the community that that process is very important in driving the overall observed mass flux. What we're finding is that that is potentially a scaled relationship. And so I'll show you some very preliminary work near the end of the talk that elucidates some insights into the complexities of that relationship and help us understand that the picture of the ocean being completely responsible for forcing all of the observed mass discharge out of these outlet glacial systems is a bit more complicated. This work was explored through a sequence of published papers as far back as 2013. In our earliest paper, our objectives were to examine these pond structures, largely because we were some of the first researchers to examine assemblages of water-filled crevasses within a major outlet glacial shear margin system. And at that time, we had no idea how much water was in these systems. Was it an amount of water that was of any real significance at all? And since we observed these ponded structures fill and drain, we wanted to understand to what degree water could actually get to the bed under the glaciological context that was that characterizes the Jakobshavn outlet glacial system. So we were interested in what these structures of pond shear margin system in these ponded shear margins were. Why are there ponds in the shear margins, given that they're so heavily crevassed? What is the spatial and temporal variability of these ponds, and how much water do they hold? Next, we start asking questions in the follow-up paper. What is the interseasonal variability of margin pond drainage, and what impact does drainage have from these features on regional ice flow? And that's where things got really quite interesting. We followed up with more work to understand what the long-term variability in the hydrologic states of these shear margin ponds were. So we embarked on a study to be able to attempt to characterize that. We moved further on to try to dig deeper into the questions about what happens when you inject water into a shear margins. What does it do in the shear margins itself, and what does it do to the ice flow in the extra marginal field? So we became much more interested in what was happening in terms of how lubrication in the shear margins can influence the mass flux into the ingested into the major outlet glacial system. So in our 2018 paper, we pursued questions about how has pond area changed over time, and what are the upper bound effects on pond drainage on regional ice flow. So we sought to try to bound the problem in characterizing what impact meltwater can have in shear margins. And ultimately, we continue to follow up in that regard with our 2018 paper, further examining this problem, and more specifically, trying to come to grips with what degree meltwater drainage in the shear margins can have in terms of its impact on regional ice flow as a function of what's happening in the subglacial hydrologic system. So I'll focus now on walking you through and highlighting some results that we had from our initial observations of systems that were focused in the Jakobshavn Isbræ shear margins. Walk you through the results where we delineated and studied these over a single melt season, and present results that are associated with the areal extent and variability of these features, as well as characterizing the glaciological setting or context in which these ponded structures were formed, and evaluate the properties and behaviors of these systems with topography, local strain rate, and the like. And ultimately, we were interested in that work and trying to wrap our heads around how much water was really potentially sitting in these ponded structures, given that we were observing them fill and drain throughout our test melt season. So I'll present the values that were associated with the estimates of the total drain volume for a significant drainage event from these ponded structures during our test melt season. So you can see here in this graphic, Jakobshavn, I'm trying to use my pointer here. We had identified a sequence of about 7 pond structures that were present along the northern and southern margins. So for those of you that may not be familiar so much with Jakobshavn, ice flow is in this direction. It has this characteristic planar snake-like shape, and the calving front is here, and the fjord is here, replete with bergy bits that are broken off from this calving front. These pond structures at this time from this image were as close to the terminus of about maybe 5 to 8 kilometers. Since this time, when this study was conducted, the calving front has substantially retreated to the point where CV1 no longer exists. So the calving front is roughly right about here now for this branch of the outlet glacial system. The very interesting thing that we noticed about these ponded structures were that they had a range of different kinds of morphologies. I'll try to sketch them very quickly here on the board. Hopefully you can see them. We had some ponded structures that were kind of traditional spatially cohesive ponds, much like what you would observe in the extramarginal fields, common for many of the supraglacial lakes that have been studied over the years. We've also had assemblages of water-filled crevasses that were kind of spatially cohesive. So they kind of constituted a cluster or a group. And then we had assemblages of water-filled crevasses and fractures that were characterized by less clustering of these features. So the important thing to note is that across these respective systems that we see highlighted here, they occupy a range of different types of systems, and they're kind of correlated with elevation in a very interesting way. It turns out that at lower elevation, where the ice thickness is less, we tend to get more spatially cohesive pond structures. And at higher elevations, such as CV6 and CV7, we get these assemblages of water-filled fractures and crevasses that are much more spatially diffuse. We were initially concerned about why water was ponding in the shear margins at all, and why their locations seemed to be fixed from one season to the next. Now, we had understood from our study in the extramarginal field of supraglacial lakes that the lakes always tend to occupy the same location from one season to the next, even though there can be variations in their drainage behavior. That is largely a function of the fact that the basal topography has been known to characterize, or known to be an important forcing on where the supraglacial depressions are that are capable of capturing surface melt. So we were interested in characterizing the basal topography to determine if we had similar kinds of controls on the location of these shear margin ponds. And that was indeed the case. It turns out that for every pond system that we analyzed, they occupied a position in the supraglacial field that was consistent with a basal depression. Now, the peculiar thing about Jakobshavn, as I noted before, is that it's sitting in a deeply incised trench. So overall, in plain view, you can see ice flowing out of the board direction. Here's the surface. And many of these pond structures are kind of occupying zones here where you've got very large gradients in the subglacial topography. That's actually really quite significant in why the mass flux that's observed for ice tracking into the ice stream system accelerate along these edges because of this very dramatic gradient in the basal topography. And that's where these pond systems are sitting, and they are of course associated with small scale undulations in the basal topography where we have these basins. During that melt season, we examined we characterized the overall, or mapped the overall change in area, inundation area of each of these water-filled crevasse systems. So the graphic here on the top right, A, is depicting in time for the 2007 melt season, the change in the aerial extent of each one of these systems. And superimposed on that was data regarding information that allowed us to be able to correlate with melt production, which were positive degree days calculated from meteorological stations that were a few kilometers north near Swiss Camp, or along the Swiss Camp research flow line. It turns out that during periods when the spatial extent or aerial extent of these ponds were expanded, that we indeed saw periods of more intensive melting. So it meant that we had sufficient conditions for the production of meltwater, even though what was a kind of a mystery was the fact that in a heavily crevassed region where these pond systems were embedded, we weren't quite sure whether or not water that was produced in the extramarginal field here could infiltrate into deep enough into the heavily crevassed region to fill up these ponds if the source of the water was that far out in the extramarginal field. And it seemed quite unlikely. So we had deduced that it was most likely that water was being produced in situ from within the crevasse system itself. And that was a very interesting observation. We didn't publish on that work, but we'd gone through looking at an analysis of the hydrologic potential surface and how water might be routed along the surface if the source for that melt was outside of the heavily crevassed regions in the extramarginal field. We also looked at the spatial and temporal dynamics of these crevasse fields in terms of their filling and drainage rates. So what you're looking at here is, in this graphic, the mean elevation associated with each of the crevasse systems, and then on the x-axis, the filling rate, which is calculated by the change in area between the first image date and the maximum or peak area achieved during that analysis period. We were interested in seeing whether or not the filling rates were associated with how high up or low the crevasse features were is a function of the varying degrees of melt that were elevationally dependent. And what we found was that that relationship wasn't quite as permanent. Even though lower elevation systems tended to experience higher melt rates and greater runoff, likely connected to the well-developed inglacial plumbing systems through moulin and crevasses, generally the filling rates increase with elevation across most of these systems. We also were interested in understanding what might be the first order controls on the drainage behavior. And we initially thought that, well, maybe we have periods of extension that might be associated with dynamics that are happening at the calving front that propagate upstream, which enhances extensional forces and allow for initiation of drainage from these crevasse systems, particularly under conditions where the presence of the spatial locations of these water-filled crevasse systems are in places that are in locales where the compressional, the magnitude of compression is more significant than in other locales along the shear margins. It turns out that in deriving the longitudinal strain rate and plotting that as a function of the drainage rate, we can see that there is some relationship, but it isn't quite a one-to-one relationship. So you can see that here in graphic B, where you've got the strain rate on the y-axis and the drainage rate on the x-axis. And so not all of the water-filled crevasses are mapping along a linear relationship between the strain rate and the drainage rate, which means that our understanding about the factors that are driving or influencing how and why these things drain the way they do is not so much related to the local dynamics, but could potentially be related more to what the characterization and capacity for the inglacial systems and subglacial systems are for evacuating water, that standing water that is present in these crevasse systems. Lastly, in this work, we examined the largest change in aerial extent for the CV2 system, which is one of our lower elevation systems, between July 8th and July 24th. In order to try to establish an upper bound estimate on the total volume of water drained. We had already characterized from satellite imagery what the aerial extent was, but we really needed to be able to constrain what the depth of fractures are in which the ponded water was residing. To produce the best upper bound effect, we estimated what the depth of those water-filled fractures were by deploying a modified Nye approximation that gives us a first order estimate of an idealized fracture potential depth that's the result of two factors. One is the ice overburden pressure seeking to close that fracture, as well as the hydraulic forcing from the water itself that seeks to keep the fracture open, in addition to the localized extensional strain. And so by deploying that NI model across the fracture system, we were able to calculate what the potential volume of water that was drained from that particular pond during the period between July 8th and the 24th. And we've gotten roughly about 0.04 cubic kilometers of water drained during that period. We were not certain whether or not it catastrophically drained it all at once, or whether or not it intermittently drained over that period. Unfortunately, at that time, we were limited by the availability of satellite imagery, because we were largely working with 30-meter resolution Landsat data, panchromatic Landsat data, which only gives us acquisitions minus cloud cover about every 16 days. What we found, though, is that that upper bound estimate is quite a bit of water. It's within the distribution, kind of on the low end, but within the distribution of the estimated total volumes of water drained from much larger supraglacial, traditional supraglacial lakes in the extramarginal field. So that became very interesting, because that meant that we were providing a sufficient amount of water at levels that were known to be able to influence localized ice dynamics in extramarginal supraglacial lake systems. So we really were excited about that. This led us then to start pursuing these other questions, which were the ability to assess the long-term hydrologic state or properties of these systems, analyze their changes in aerial extent at the decadal timescale, and evaluate the drain states of these systems. Now, it turns out that in the capacity to be able to do this, we were very eager at that time to be able to try to give us the first order picture on what the long-term variability state of these water-filled crevasse systems were. And since we were the first to try to characterize these systems, it became difficult from optical imagery with constraints due to cloud cover to be able to aggregate imagery across multiple imaging systems to be able to delineate the boundaries of these supraglacial systems over a long period of time. The utilization of automated routines to do that are limited by the fact that many of the optical systems that we were working, data from those optical systems we were working with, were resolution limited over a locale where the variability in the surface properties that are associated with these crevasse systems weren't well resolved by the satellite data that we had available at that time. Given that constraint, we opted to simply characterize a hydrologic state. And so by looking at satellite data from multiple optical platforms, we just simply recorded whether or not it was water filled or drained on a particular date. And we did that over a 10-year period, over a decadal period. And that really gave us a very interesting and much more comprehensive picture at what the total field states were over this decadal period. We used data from Landsat 7, Landsat 8, Google Earth historic imagery, imagery from the Polar Geospatial Center, which was high resolution imagery, meter scale imagery, data from EO1, ALI, SPOT, and ASTER. What you're looking at here is a graphic of a breakdown over the melt season from May to September for the occurrence states of field states. So these were the total numbers of states where we observed water to be present in each one of those water-filled crevasse systems. What's obvious is that obviously we have the highest occurrence of field states during the peak period where the melt season is most significantly the warmest. And then we have a tapering and a decrease in those field states as the melt season progresses. Probably the two most interesting things that we got out of this work, assessing this from 2000 to 2015, was that we were starting to observe filled states later in the melt season, clear through the end of September and some into early October, which is not shown here, even though it wasn't the largest proportion of the total number of filled states. The other very interesting thing was that several of these water-filled crevasse systems filled, drained, and filled again. So we had multiple occurrences of filled states, which means that we had some very interesting dynamics that allowed for the initial capture of water and drainage, and then capture again in drainage, which means we got more than one instance of meltwater injection in one season into a particular part of the shear margin system. Next, and most importantly, we went on to try to understand what happens when shear margins are hydrologically weakened. What are the potential impacts on mass flux through the marine terminating outlet glaciers as a result of drainage into these shear margin systems? We'd have to start in this case with our first order hypothesis about what we thought the potential impact would be. We kind of thought through this initially before we embarked on trying to constrain and understand what the real impacts were from drainage from these systems. The two places where we considered was, one, what is the influence on flow within the main trough of the ice sheet or outlet glacial system here? And then the other question was, what influence does drainage potentially have on acceleration in the extramarginal field? So I keep using this phrase extramarginal, and so that effectively means ice outside of the shear margins proper, and effectively the ice that's adjacent to the outlet glacial system. What we had initially theorized was that if you had drainage within the shear margin, so you have drainage that potentially delivers water directly to the bed, that you get the initial onset of lubrication that enhances upstream longitudinal stresses beyond the shear margin into the extramarginal field, which ultimately enhances discharge and mass flux into the ice stream system. Ultimately, what that accomplishes is the dilation of the catchment area across which Jakobshavn is drawing ice into the main outflow system. So that is what we thought would be the overall influence on lubricating within the shear margins. An attempt to try to constrain that was to use some first order simple models, numerical models, to try to bound the problem. So we worked within ISSM to create diagnostic models that deploy our standard conservation of linear momentum equations, discretized over mesh at 200-meter mesh resolutions over our study area, which encapsulated the region where all 7 of these pond structures were mapped. We used a SteadyState model deploying a shelfy streamy ice flow model, which assumes vertical shearing is negligible, and that our boundaries are described and prescribed by surface and basal topography, geothermal heat flux data, and surface mass balance for our surface forcing for the surface, as well as surface velocity, measured surface velocity data to constrain ice movement. We did deploy a very rudimentary Coulomb-style basal friction law and a thin layer basal water scheme. So effectively what we assumed was that at the base of the ice sheet, we have a very thin layer of water, and the location and duration for the transient models that we had ran later, that I'll describe later, within the aerial extent, the cumulative aerial extent for all of the melt seasons where we mapped the aerial extent for each of the water-filled crevasse systems, we lubricated the bed using this thin water scheme to understand what the influence of of lubrication would be in those locations on regional ice flow. And we examined changes in velocity along these analysis flow lines. Now you'll see that flow lines 1 through 4 here in the graphic are situated in the southern margin. And that's because Jakobshavn has a very particular way in which it sucks ice in. The projected area along the southern margin is able to draw ice in over a much larger extent than the northern margin. So if you were to look at Jakobshavn in this case in plain view, the northern margin ice is actually dragged along. So the outboard ice here is pulled along and then is injected into the ice stream within a fairly narrow zone. Conversely, in the southern margin, ice is being pulled along and ingested right into the ice stream along a much larger arc. And so the reason why we focused on this section of the ice stream, the southern margin, was in large part because we just had a much larger potential influence on the mass flux. So our steady state models demonstrated that ice flow gets amplified within 10 kilometers of the ice stream margins by as much as 20%, which is equivalent to an increase of about 0.6 gigatons a year of additional ice mass drawn into the ice stream system and ultimately discharged into the fjord. This is associated with acceleration within the ice stream system within the main trough on the order of about 4%, and could be as high as 12% depending on how large of the lubrication area you delineate from any one of these outlet glacial systems. And so you can see the chart here that breaks down what our estimates of what the steady state mass fluxes are, both in the northern and southern margins. And of course, the northern margin is much smaller than the southern margin. And then these were the crevasse drainage mass fluxes that were the result of lubricating within those spatial extents of those saturated crevasse systems, if under the circumstance where we lubricated them all at the same time. Now you might ask the question, is that realistic? Given that in previous graphics, we showed that the temporal variability of the drainage from each of these systems were not coordinated. And so that is true. This is indeed an oversimplification of the problem, but it allowed us to be able to bound the problem in such a way to be able to get these first order estimates. We also were interested in measuring what the acceleration was in the extramarginal field. So using Landsat OLI data, we were able to extract surface velocities at high temporal resolution along those analysis flow lines. And so in these panels, A, B, C, and D, which you can see is speed along the y-axis and time along the x-axis. And then the colors are associated with the distances away from the shear margins. So the reds are close to the shear margin, and then the blues are farther away. And so obviously you can see that we have higher speeds near the margin, and then lower speeds that drop off substantially as you get farther and farther away from the margins into the extramarginal field. That's consistent with our numerical models, demonstrating that much of that acceleration is largely contained within the first 5 kilometers or 4 kilometers of the margin, and then exponentially drops off as you move farther away from the shear margins. Also during that period, we correlated those measurements with drainage. So we looked at the average velocity over the entire flow line at each time increment compared with the average velocity for the entire melt season, which we designated from May 31st to September 30th. What we were looking for was to see whether or not along any one of those flow lines, if we saw average increases in anomalous acceleration beyond the background summer mean, that are associated with periods in which we observe drainage. It's a little bit tricky, in large part because the data measured between every 16 to 96 days does not provide us with a consistent temporal sampling along the analysis period. But we did have some results that indicated that there were some increases in anomalous velocities that were associated with this period when we had a group of many of those saturated crevasses drain roughly around the same time. So lastly, we have to ask ourselves, what does this look like in terms of this process related to a much broader set of dynamics that are happening that are influencing the ice sheet system as a whole? And this gets to this issue about how much what's happening at the calving front really matters in the extramarginal field. And so this has actually been a topic of some debate. My friend and colleague, Johannes Bonzio, published a GRL paper about 3 or 4 years ago, where he responded to us, our sequence of papers, demonstrating that these crevasse ponds could influence the mass discharge in the extramarginal field, accelerating the amount of ice being drawn in the Jakobshavn. His response was, you know, if you just heavily crevasse and damage the shear margins with crevasses, that you reduce the capacity for resistance along the shear margins such that perturbations at the calving front can propagate much farther upstream and far afield into the extramarginal domain much more readily, which means that much of the acceleration that's observed in the extramarginal field could be largely explained by what's happening at the calving front. And we know that that's enhancements in calving are forced by its coupling to the ocean. And I responded and told him, well, the way in which you arrived at that conclusion was that you had both spatially and by magnitude overprescribed the amount of damage along the length of Jakobshavn. In fact, what he did is he linearly scaled the magnitude of damage from the calving front all the way upstream. And of course, by looking at Jakobshavn, you can see that it has this snake-like planiform, which means that you've got large variations in strain along the length of that, such that the magnitude of crevassing associated with variability and extensional forces should produce variations in the magnitude of fracture depths along that length. So I told him, I think you overprescribed the amount of damage spatially. And ultimately what you did is in your model, you've overprescribed the effect of that damage. And you've basically parameterized out the effect of drainage from these shear ponds. Plus, our analysis is based on direct observations of ponded water. You can't readily see how much damage is in the shear margins generally if you just go based on the planiform representation of the distribution of the fractures. But you can see ponded water and you see it fill up and drain, which we've characterized over time. So we wanted to revisit this issue about what is the real relationships or potential relationships between how the extramarginal field is responding to what's happening in the shear margins versus what's happening at the calving front. And so again, looking at our analysis along the 4 flow lines that were part of our initial study, we extended those out a bit in order to look at the far field and deeper into the extramarginal field, roughly about 20 kilometers or so beyond the shear margins. And what we find there is an assemblages of our traditional supraglacial lakes, large supraglacial lakes that are the focus of many, many studies that have been done over the last 10 years or so. We've taken a look at more recently acquired high temporal resolution 16-day sentinel data. And so in the graphic here, you're looking at anomalies along one of our flow lines. in velocities or ice speeds captured along those flow lines or extracted from this particular flow line 1, on these dates along the y-axis. Here in the lower graphic, you can see kind of a profile of that of the ice surface elevation and the bed along that flow line. So basically, this region here is closer to the margin, at the margin, and then as you move along the x-axis, you're moving farther and farther away. Panel B shows the change in aerial extent at the calving front, which are associated sequentially with retreat and advance events. So the red bars are associated with this particular time frame, a 6-week time frame, where you had a retreat of the calving front. And then the gray bars here are associated with advances. Panel C is associated or showing you the far field supraglacial lakes. So you can see when they fill up and when they drain. So you can see the drainage behavior there. And then panel D at the end is showing you the temporal behavior and the aerial extent of the shear margin ponds that we've been studying. The important take-home message here is that these velocity anomalies or speed anomalies at the 6-day time interval for the 2017 melt season from June to September show that the velocity anomalies are not correlated with calving all the time. And the far field anomalies may actually be an important factor at that smaller time scale in influencing the overall change in behavior of the ice flow along these flow lines from the margins into the extramarginal field. We started to ask the questions, to what degree could we explain what is happening with these far field supraglacial lakes that can contribute to some of the accelerations that we saw much farther away from the ice stream than and which is also uncorrelated with what's happening at the calving front. So we deploy the use of Shakti, which is a evolving subglacial transient hydrologic model. At the first phase, we're allowed, we set up Shakti to be able to provide us with an estimate of a subglacial effective pressure. Then we run a diagnostic ice flow model for the baseline case of no water at the bed. And then we run an additional model for a diagnostic model, ice flow model with drainage from the water field, from the extramarginal pond here at these locations. And in a transient fashion where we inject melt water continuously to the bed for 10 days, for a 10-day duration. The Shakti model allows us to be able to model the evolution of the subglacial hydrologic system over that time period from linked cavity systems to a distributed system. So we're able to get an overall understanding of what impact drainage and lubrication from these deep extramarginal ponds might have on ice flow along our flow line. So here's the initial results from that analysis. What you can see here is this is the center in which we've got the epicenters or the centers of the deep field extramarginal lakes. It's actually hard to see their location, but they're largely clustered around here. This green line is flow line 1. And you can see that we've got accelerations as high as 50% in the deep marginal field, with a drop off as you get closer to the margins of the ice stream, which are here. But these accelerations, the location of these accelerations are consistent with the measured velocity anomalies in the previous graphic here, where we've got, upwards of 80 to 100% in enhancement in ice flow really far away from the calving front. So what this elucidates is that at the weekly to monthly time scale, the relationship between what's happening at the calving front and what's happening in the extramarginal fields is probably much more complex than the calving front, than calving being responsible for propagating all of the mass flux that's observed in the far field. Now, what this actually hints at is something really quite interesting in terms of scaling as a function of time and space. Most of the correlations between the dynamics at the calving front and accelerations, in the deep far field, much farther upstream into the ice sheet system beyond where we've been doing our analysis, is that that relationship has been established from velocities measured over much longer time frames. So we might be seeing an interesting scaling relationship where subscale processes like supraglacial lakes, localized supraglacial lakes, and water pondage structures within the shear margins have a much more profound impact on the dynamics of the ice fluxes over those shorter time frames, but that the integrated influence of those factors over larger areas and longer time periods produce the impression that the calving front, the dynamics of the calving front, are directly correlated with producing acceleration very far afield. And the reason why that's a little bit of a stretch is because very early work by Ian Joggin had demonstrated that a mass perturbation at the calving front propagates upstream as a diffusive kinematic wave, but that it becomes very diffusive and drops off, quite substantially in amplitude by upwards of only 15 to 20 kilometers upstream away from the calving front. That's nowhere near far enough to be able to explain over a given time frame the accelerations that are observed much farther away. So I think there's a very interesting a possibility for expanding the discussion about the relationship, the scaling relationships between these various factors that are driving or perturbing the ice sheet system. Now, before I conclude, really the importance on trying to understand the degree to which these water-filled ponds and crevasses in the margins are important in any way is really about what's happening at the bed and how the subglacial hydrologic system is responding. What you're looking here in this map is showing the distribution of the hydropotential surface at the bed associated with each of the 7 water-filled crevasse systems. And what you can see is that we've got relatively low hydropotential gradients for CVs 3 and 6 and 7, and higher for 1, 2, and 4. And so ultimately, we were concerned looking at this about to what degree is the drainage of any one of these ponded systems influencing shearing along the length of the shear margins if water is more readily able for some of these systems to travel more along in the subglacial hydrologic system during periods when that system is able to evacuate that water from the initial entry point along the shear margin, or longitudinally along the shear margin, parallel to the shear margin, versus redirection and subglacial hydrologic drainage into or deeper into the trough. And so what that might elucidate is that drainage from these systems may have a much more profound and much longer lasting and much more spatially expansive influence if the lubrication effect is able to propagate and lubricate a much larger area across which the shear margins comprise. And that harkens back to some of the initial modeling studies that we did to try to constrain the initial impact of drainage from these systems, because what we found was that our largest acceleration, upwards of 30%, could be observed if the area of lubrication is expanded. And so one way is that you can have a larger area of water being proliferated as a function of increases in the magnitude of melt within these assemblages of crevasse systems. Or you can have meltwater that has drained and entered in a relatively spatially limited location, but evacuate along the length of the shear margins, lubricating more of the shear margins and further enhancing the weakening of shearing. So in conclusion, kind of accumulation of summarizing all of the work that we've done over this period, we think we've established that there's enough water in these water-filled crevasse systems to influence the overall force balance of an outlet glacial system like Jakobshavn. Hydrologic infiltration could weaken the shear margin through basal lubrication. We've determined that enhanced extramarginal ice acceleration can occur between 7 to 10% and can be as high as 30% with an increase in the basal lubrication area. The magnitude of the impact decreases with distance away from the margin, and the magnitude of impact is largely dependent on the basal hydrologic configuration. Again, I harken back to the statement I made about scaling. This work has incrementally led us into exploring more and more research questions, and I think the most profound and most interesting research question that we're on the precipice of it is about scaling. And this really is important in our ability to prognosticate future contributions of the Greenland ice sheet to sea level rise. And the reason why is because contemporary ice sheet models that are coupled to or embedded in GCMs lack the ability to resolve subscale processes, and the potential transfer of information from subscale to larger scale at which these GCMs operate. So I think getting a hold, or getting our hands wrapped around the potential scaling problems is a really, really significant aspect of this work. And I think that is the direction in which myself and many of my colleagues are starting to think about in terms of improving our understanding and how the ice sheet system is responding to a warming climate. I want to thank you all for your time and thank my collaborators. And I now open up this time for questions. Thank you again.
Thank you, Derrick. That was a very interesting, insightful presentation of the impact of those drainage down to the bed. So we don't have a lot of time. Maybe just one brief question. If someone has one, we could do that.
Hey, this is Duncan. So you mentioned that a lot of the melt was being generated locally in the crevasse zones as opposed to flowing in. Is there anything about the topography, i.e. the roughness of the crevasses that might favor melting locally? Have you looked into that?
It's a really good question. So we had done some work, and it hadn't been published, where we looked at that CV2, that largest crevasse system, which is CV2. And it turns out it is in a localized depression, as I noted, as a result of the presence of a basal topographic depression. This is kind of a simplified representation of this, so I'll try to superimpose what the morphology of the crevasses kind of look like here, but it's not exactly like that. So you've got in cross-section this assemblage of the crevasses, and then they're water filled. In this case, CV2 was kind of uniformly water filled and had more of a morphology similar to a traditional supraglacial lake. Hopefully you can see that. Try to turn that. So we looked at kind of in plane view. Flow lines or propagation of water lines within this basin. And we tried to create a very simplified infiltration surface or near subsurface infiltration model under the assumption that water could potentially be produced in situ by solar insolation near the upper part of the crevasse initially, with some localized production of melt where the crevasses are not quite as deep out here, so that you got some infiltration, surface partitioning, and then some subsurface infiltration that allows for water to percolate through a complex intercrevasse fracture system to the point where you fill the basin up from the sides and up like this. And so even though we hadn't completed that work, we speculate that we think this is the way in which water could potentially fill up these basins. For one that has this kind of morphology, this is probably a bit more complex for those that are more spatially separated assemblages or clusters of water-filled crevasses, and drive why these systems are able to fill up. I'm sorry, could you? I might have missed an aspect of your question that I didn't address here, but.
No, I think that gets into it. Yeah, it is a little bit more jagged than the traditional background that most of the ice sheet is. So yeah.
There has been some recent work in characterizing surface roughness from ISAT-2 data. Actually, I just recently read a paper that was published on that. There had been previous work done by ATM, airborne ATM measurements during the Ice Bridge mission, and assessed that overall the total amount of surface roughness associated with the marginal areas have increased over time. But that is probably correlated with the fact that, you know, Jakobshavn up until fairly recently had an increasing trend in acceleration. So we probably were seeing, you know, on overall an increase in extension as mass was just being shedded at the front. Jakobshavn has slowed down a bit. And so I have the most recent ISAT-2 results show that it was really a technology demonstration to see whether or not photon counting based altimeters have the capacity to characterize the morphology of these, or the near surface morphology of these crevasses, which the data suggests that's possible. But I haven't gone back to look more closely at what the relationship is between the roughness distribution from ISAT-2 and the other properties that we've characterized from these systems. So that could be a place where we're considering to do more work.
Well, thank you, Derrick. So we are running against the time, but we have, I mean, people and especially students who will have the opportunity to ask more questions during the lunch, which is happening right now in 5-10 minutes, so that we have the time to do our things. And you have the link for the lunch in the chat, and you also have the link for the lunch in the Google spreadsheet. Thank you again, Derrick. That was great. And we'll see you after that.
Appreciate your time all. Thank you very much.
Goodbye.